Today we're going to discuss algorithms for answering questions about regular languages, or really about the representations for the languages, such as finite automata. The questions we can resolve for finite automata include many we cannot resolve for programs in general. Examples include whether a given string is accepted by a given automaton, that's the membership problem, or whether a given automaton accepts any string at all, the emptiness problem. As part of our discussion, we're going to prove an important theorem called the pumping lemma that lets us show certain languages not to be regular. Automata theory talks about many different classes of languages, including context-free languages, recursive and recursively enumerable languages. We're going to meet each of these classes, but for the moment we know only one class, the regular languages. When we investigate a class of languages, there are two important issues. The first is decision properties. We shall see that there are many questions we might like to ask about a language, or rather its representation, such as whether it is empty, finite, or infinite. It is good to know there are algorithms to answer such questions, at least for the regular languages. Unfortunately, as we meet larger classes of languages, we find that in general, the larger the class of languages, the less likely there is to be an algorithm to answer a question about languages in that class. The second important issue is closure properties of the class. These involve applying operations such as union to languages in the class. We're going to defer the discussion of closure properties to another lecture, although I'll give you an example on the next slide. Closure properties are statements that when we apply certain operations to languages in the class, the result is also in the class. For example, we say that a class of languages is closed under union if given two languages in the class, the union of those languages is also in the class. So if I have two regular languages, I can represent them by regular expressions and connect those expressions by a plus with the appropriate parentheses to get a regular expression for their union. Similar constructions work for their concatenation and closure. Now let us address the main topic of this lecture, decision properties of regular languages. We've used both formal and informal ways of describing languages. The formal ways include finite automata and regular expressions, each of which defines a language by a precise mathematical definition. But we have also described languages informally by prose statements and set formers, such as this, or even more informal statements like this. However, you can't answer questions about a language unless you have a formal description. For instance, we will talk shortly about testing whether a regular language is infinite given one of its formal representations. It looks like the last of the informal descriptions describes an infinite set, but does the word some mean any, or some one particular number like 10, for example, that I have in mind? Thus, we're only going to use formal descriptions of languages when we talk about algorithms for deciding things about those languages. Thus, a decision property for a class of languages is an algorithm that takes a formal representative of the language. The algorithm answers some particular question about the language, such as whether or not the language described by the representation is empty. Here are a few examples of why we might be interested in decision properties of regular languages. Both involve protocols represented by automata. If we ask whether the language of such an automaton is finite, we are in effect asking whether the protocol it represents is guaranteed to terminate. Or if we make the final states of the automaton be error states, then asking if its language is empty is tantamount to asking whether the protocol can fail. And remember, we couldn't answer either of these questions about programs in general, so we couldn't get the answers to these questions about protocols by looking at the code that implements them. Another use for decision properties of regular languages involves minimizing their representations. For instance, DFAs are a good representation for certain kinds of digital circuits, those that have memory. We usually want the smallest circuit to accomplish a task, and a good first step is to find a DFA that does what we want and has the smallest number of states of any DFA for the same language. It turns out that we can tell whether two DFAs are equivalent, that is, whether they define the same language. That lets us find a minimum state DFA equivalent to any given DFA. Again, we could do none of this for programs in general. We can't tell whether two programs do the same thing, and we can't find a smallest equivalent for a given program, even though we know in principle that one must exist. The membership question for regular languages is answered by an algorithm that takes a DFA and a string and tells whether or not the string is accepted by the DFA. The algorithm is the obvious one. Simulate the DFA on the input. Here's an example. It's something we've seen several times before. Each time I show it to you, I use a different style of presentation, but the idea is always the same. Here is the DFA for strings without consecutive ones, something which I know we've seen before. And the input string is 0, 1, 0, 1, 1. That obviously has consecutive ones, so it shouldn't be accepted. Well, let's see what happens when we simulate it. We read a 0, we stay in A. When we read a 1, we go to B. Read a 0, we go back to A. Read a 1, we go to B. Read another 1, we go to C. When we simulate this DFA on the input, we see that indeed the string gets the automaton to state C, and it is not accepted. Now you might wonder, what if the regular language were represented by an NFA or a regular expression, for example? Then you first need to convert the representation to a DFA and then simulate the DFA. It is possible to convert from any of the four representations we know about to any of the others using this circle of conversions. So doing might exponentiate the size of the description, but there is still an algorithm to do the conversion, and that's all we need to show there is, for example, an algorithm to tell, given a regular expression and a string, whether the string is in the language of the regular expression. Generally, proofs of closure or decision properties require either a DFA or a regular expression, by the way. The emptiness problem is, given a representation for a regular language, does its language contain any string at all? Okay, we're going to assume the language is represented by a DFA. Obviously, if by some other representation, then convert it to a DFA. Finding reachable states requires a breadth-first or depth-first search from the start state. I'm not going to assume you are familiar with these search techniques, but it is fairly easy to think of some way of searching a graph from a single node by following all arcs out of the node and marking those nodes you have visited. Then, follow arcs out of the nodes you visited and mark any other nodes you visit. Keep doing that until you cannot mark any other nodes. The marked nodes are those that are reached from the start state on some input. If at least one final state is marked, then the DFA accepts at least one input. If no final state is marked, then it is impossible for the DFA to accept anything and its language empty. Here is an example. Here's your start state. We might mark these guys, maybe mark these guys as we go. But if all your final states are out here and never get marked, then obviously, no matter how complex this automaton is, you can't reach your final state and you can't accept anything. Now, if you have an automaton with 3 states, it's pretty easy to tell what's reachable and what isn't. But if you have 1,000,000 states represented by some table, then it is hardly easy to tell. But fortunately, we have a straightforward search algorithm regardless how large the automaton or graph is. Now let us take up a more difficult problem, but one that we can still solve. We'd like to know whether or not the language defined by a DFA is finite or infinite. The first fact we're going to prove is that if the language of the DFA contains any string of length n or more, where n is the number of states of the DFA, then the DFA contains an infinite number of strings. Surely, if the DFA doesn't accept any string of length equal to or greater than n, then it accepts only a finite number of strings. However, it doesn't seem feasible to test membership for all input strings of length n or more, since there are an infinite number of them. Can we ever finish? If not, then we really don't have an algorithm for testing infiniteness. But as we shall see, it is possible to limit the length of strings we have to test to twice the number of states. So we have a really large and ugly but finite task, and we really do have an algorithm. So let's try to prove the point we need, that if the DFA accepts any string whose length is at least the number of states n, then it accepts an infinite number of strings. First, observe that a string of length n or more has at least n plus 1 states along its path. For example, a string of length 2 has 3 states on its path. Here is a typical picture we might have. String AB looks like that. Notice no matter how many, well, the number of symbols in the string is the number of arcs, and there's always one more node than there are arcs in the path. That's why there will be n plus 1 states for a string of length n. Okay. Now, if there are only n different states, and there are n plus 1 states along the path, then 2 states along the path must be the same. That's called the pigeonhole principle, you might remember. Here's a picture of the path for string W, which we're breaking up as x, y, z. X is the prefix of W that gets the DFA to the first state that repeats on the path, which we call state Q. It's right here, of course. Then Y is the part of W that gets the DFA back to Q for the first time. That is, the end of Y is the second occurrence of Q. Notice that therefore Y cannot be the empty string, although X or Z might be. Finally, Z is the rest of W, and we know it gets the DFA to a final state because W is accepted by the DFA. Notice that the path labeled Z may have states that also appear earlier, but it doesn't matter. The important thing is that we identified the first repeating state Q. We claim that X, followed by I repetitions of Y, followed by Z, is also accepted by the DFA for any integer I. To see why, X takes us to state Q, so we could, for example, go like this. Okay. And then we could skip Y altogether, just follow Z, and we get to a final state. That tells us that XZ is in the language. Or we could follow X to state Q. We could go around loops many, many times, and then finally go off following Z, and again get to the final state. Or after I uses of input Y for any I, however large, we follow input Z and we accept. This proves that X, Y to the I, Z is accepted for any I. Remember that Y cannot be empty, so all these accepted strings are different. Thus the DFA accepts an infinite number of strings, one for each I. Remember, we still do not have an algorithm because we can't test the infinite number of strings of length equal to or greater than n. However, we don't have to, because it is sufficient to test strings of length between n and 2n minus 1, and there are a finite number of such strings. When we prove this statement, we shall at least have an algorithm, although it is a rather time-consuming one. Now, we picked Y to be the first cycle on the path, so the length of xy cannot be greater than n. That is, some state within the first n plus 1 states on the path surely repeats. We also know that if the length of y is at least 1, so y lies between 1 and n, then if w is the shortest accepted string of length at least n, then we claim that w cannot be as long as 2n. For suppose it were. Now xz, as we know, is another accepted string, and the length of xz is the length of w minus the length of y, and the length of y is at most n. So the length of xz is at least n. That means that xz is a string shorter than w, yet at least n in length, and it's also accepted. But we assume that there was no string accepted that was shorter than w and also of length at least n. As a result, given any really long string w that's accepted, we can keep taking out pieces of length between 1 and n, that's the y in each of these diagrams, and we just keep throwing them away, and eventually what's left of w will be between n and 2n minus 1. So the algorithm to decide whether a regular language is infinite is to construct a DFA for it and let the DFA have n states. Test all the strings of length between n and 2n minus 1 and say infinite if any of them are accepted. Otherwise, say finite. This is a terrible algorithm. If there are k input symbols and n states, then the number of strings we have to simulate is about k to the power 2n. That is a lot of work, and there is a much more efficient algorithm, one that takes time proportional to the number of transitions, that is k times n, if implemented right. I wanted to give you the argument about the lengths of strings because it's important when we take up the pumping lemma, a technique for showing languages not to be regular. However, let's sketch how the efficient algorithm would work. We already discussed searching forward from a node in a graph to find all the nodes you can reach. So we can eliminate the states that are not reachable from the start state. We then want to eliminate states that don't reach a final state. This algorithm is the same, except start by marking the final states and follow the arcs backwards. Now there's an elegant algorithm for finding cycles using depth-first search that takes time proportional to the number of edges or transitions. I'm going to trust that you will meet this algorithm in a course on algorithms and data structures if you haven't already done so. However, here is a simple way to test for a cycle in a graph. It takes time proportional to the number of nodes or states times the number of arcs or transitions. We're going to do the same thing for each node n. Starting at n, search forward until you either can reach no more nodes or you discover that you can reach n. That is, here's node n, we explore forward from it, and if we're lucky, at some point we reach a node that has an arc back to n. Okay. If you can reach n, then you have a cycle and we can conclude the language of the DFA is infinite. If not, try the same process from another node. If you exhaust all the nodes as starting points and you still haven't found a cycle, then there are none and you conclude the language is finite. This is a good time to introduce the pumping lemma for regular languages because we have essentially proved it during our analysis of the infiniteness problem. Here's the statement of the pumping lemma. For every regular language L, there is an integer n, which happens to be the number of states of some DFA for L, such that for every string W in L whose length is at least n, we can break W into W equals x, y, z, where y is the label of the first substring of W that goes from a state to the same state, as we saw in the previous slides, such that three things are true. First, the prefix xy of W is short. It is of length at most n. We assure that by making y be the label of the first cycle we encounter. Second, y is not the empty string. We assure this because y connects two different occurrences of the same state along the path of W. And lastly, x, y to the I, z is in L for all integers I. This statement is particularly complex because it is of the form for all there exists for all there exists. But here's how we use it. Think of a game played between you and an adversary. You pick the language L that you want to show is not regular, and suppose the adversary claims it is regular. Then the adversary has to provide the there exist parts while you play the for all parts. You've already picked L. Now the adversary has to pick n. He can pick a number as large as he likes, but once picked, it is finalized and the game proceeds. Now you get to pick the string W, subject only to the constraint that it is at least as long as n, the number the adversary picked. Next, the adversary has to break your W up into x, y, z, subject to the constraints that the length of x, y is at most n and the length of y is at least 1. You win the game by picking an I such that x, y to the I, z is not in L. However, in a proof, we don't know what moves the adversary will make. Thus, to win, we need to cover all possible moves. That is, we know the picked n, but we don't know n's actual value, so we must pick W in terms of n. Similarly, we know W equals X, Y, Z, but we don't know exactly where Y is, except that it is not empty and it is among the first n positions of W. Thus, our argument that X, Y to the IZ is not an L must work for any of these possible Y's. Now, let's see an example. Let us pick this language as L. It is the set of strings consisting of some number of zeros followed by the same number of ones, and we have claimed before that it is an example of a non-regular language. Now we're going to prove it. Now the adversary picks n. We don't know what n is, but we know it has some fixed value. Now we get to choose W in terms of n. And we pick W equals 0 to the n, 1 to the n. That is n zeros followed by n ones. But then the adversary gets to break W into X, Y, Z, and we don't know exactly how it is broken. But we know enough about X, Y, Z to show that there is some string, in particular the case I equals 2, that the pumping lemma says has to be in the language L. But obviously it isn't, because it has more zeros than ones. That is, we know that Y, being part of the first n positions of W, can have only zeros. Okay, so two Y's have more zeros than one Y, and the number of ones, which are all contained within Z, doesn't change. We next take up the question of testing whether two regular languages are the same. We suppose we're given representations for two languages, L and M. Whatever representation we're given, we convert to DFAs, and then we have to combine those DFAs into a single DFA that in a sense runs both DFAs in parallel. We call it the product DFA. Suppose these two DFAs have states Q and R. In the product DFA, the states are pairs, one state from Q, the other from R. The start state of the product DFA is the pair consisting of the start state from each DFA. For the transitions of the product DFA, suppose we have a state that is the pair QR, and suppose A is the input symbol for which we want to figure out the transition. We look at the transition function for the first DFA, say delta L, and we see where Q goes on input A. So here's Q, and on input A it goes to some state like that. Then we look at the transition function for the second DFA, say delta M, and we see where R goes on input A. So here's R on input A, it goes somewhere here. Okay. Then in the product DFA, the transition from the state QR on input A is to the state pair that is whose first component is delta L of QA and whose second component is delta M of RA. That is, we simulate the two transitions in parallel. Here's a little example. Here are the two given DFAs. We'll call this the orange DFA and that the purple DFA. And here's the product DFA. It's obviously here. For example, let's figure out the transition from AC on 0. So here's state AC, and I look in the orange automaton, A on a 0 goes to A itself, and in the purple automaton, C on a 0 goes to D. So the combination AC goes to AD, and you see that transition here. For another example, where does AD go on input 1? Well, the orange automaton says A goes to B on 1, and the purple automaton says D goes to C on 1. So on 1, AD goes to BC. That's this transition there. The algorithm for testing whether two DFAs are equivalent, that is, whether they accept the same language, begins by constructing the product DFA. Make the final states of the product DFA be all those pairs such that one is a final state and the other isn't. If string W reaches one of these final states in the product, then W is accepted by one of the original DFAs and not the other. Thus the two languages are not the same. Only if the product DFA with this selection of final states has an empty language are the two DFAs equivalent. Here's an example. AC is made a final state because in the original automata, C is final and A is not. Likewise, BD is final because B is final, but D is not. We now see that the two original DFAs are not equivalent. It happens that the final state BD is not reachable from the start state, so there are no strings that the orange automaton accepts, but the purple one does not. However, AC is also a final state, and it is obviously reachable from the start state because it is the start state. That is, the empty string distinguishes between the two automata. The empty string is accepted by the orange automaton, but not the purple one. A related question to ask about regular languages is whether one is contained in the other. The test is in a sense one half of the equivalence test we just saw. Start by building the product automaton. But we have to define the final states differently. How would you do that? That is, L is not contained in M if and only if some string W that is in L is not in M. Such a string would get the DFA for L to a final state, but would not get the DFA for M to a final state. So the question of containment is the same as the question of whether there is any string W that gets the product automaton to a state QR where Q is final and R is not. Here, B is the only final state of the first automaton and D is the only non-final state of the second automaton, so only BD is final. As we observed before, BD is not reachable from the start state. It has arcs out but no arcs in. Thus the language of the product automaton is empty, and we conclude that the language of the orange automaton is a subset of the language of the purple automaton. Next, we're going to attack the problem of, given a DFA, find the equivalent DFA with the fewest states. There is an obvious dumb algorithm. Just consider all the DFAs with the same input alphabet, but a smaller number of states. There is a huge but finite number of such automata, so in principle we can solve this problem. This time we're not going to dwell on the bad algorithm. We'll talk you through the good algorithm immediately. The key idea is to build a table of pairs of states and figure out which pairs are distinguishable, in the sense that there is some input string that leads one of the pair to a final state and the other to a non-final state. Otherwise, states are indistinguishable and they can be merged into a single state. Here's the tennis automaton we saw way back at the beginning of the course. Now, let's look at the states 40, 30 here and add in. Input S takes them both to an accepting state, that is, server wins, and input O takes them both to deuce, right, here and here. Thus, no further inputs could ever distinguish 40, 30 from add in. Similarly, 30, 40 and add out are indistinguishable. Now we can deduce that 30 all, that's here, and deuce are also indistinguishable. On input S, they go to 40, 30 and add in, respectively. That is here, 30 all goes to 40, 30 on S, and deuce goes to add in on S. But we know that those two states are indistinguishable, so we'll never be able to distinguish 30 all from deuce by a sequence beginning with S. And further, on input O, well, 30 all goes to 30, 40, and deuce goes to add out, and we said we can't distinguish these two states. So there's no string whatsoever that can distinguish 30 all from deuce. Okay, we're now going to talk about how we find the distinguishable states. The basis is pairs that are distinguishable by the empty string. These are the pairs that have one final and one non-final state. For the inductive step, we can mark a pair QR if these states go at some input A to distinguishable states. That is, say here is Q, and on A goes to some state. I don't know what it is, but it's certainly delta of Q and A. And here's R, and it goes on A to, again, some other state. I don't know what it is, but it's a delta of R and A. And then these two states on input W, we'll say that this one goes to a non-final state, and that goes to a final state on input W. Okay. Then I claim AW distinguishes Q from R, because obviously Q goes on AW to a non-final state, and R goes on the same AW to a final state. After no more marks are possible, the unmarked pairs are equivalent and can be merged into one state. This point may be obvious, but we're going to need it in what follows. If there's no string W that distinguishes states P and Q, and there's no string that distinguishes Q from R, then how could some string W distinguish P from R? That would mean that there's some string W leads one of P and R to a final state and the other to a non-final state. Let's say R leads to a final state. So here's W leading P to a non-final state, and here's R, and on the same W gets to a final state. But then W also distinguishes Q from either P or R. So here's Q, and W leads it to some state. Okay, so let's say that W leads Q to a final state. Then W distinguishes Q from P, because here P on W goes to a non-final state, Q on W goes to a final state. Okay. If Q goes to a non-final state, then it doesn't distinguish P from Q, but it does distinguish R from Q, because Q would then go to a non-final state while R goes to a final state. Incidentally, distinguishable is not transitive. It is quite possible that W distinguishes P from Q and also Q from R, but does not distinguish P from R. For example, W could lead both P and R to final states and Q to a non-final state. We're now going to use the table of indistinguishability to merge states that are indistinguishable. That gives us the minimum state DFA, although we must be careful to remove at some stage all the states that are not reachable from the start state. Okay. Suppose we have a set of indistinguishable states, say Q1 through Qk. We're going to replace them all by a single state that behaves as they all do. Call the representative Q. It can be one of the Qi's or some new name we create for this purpose. On any symbol A, all the indistinguishable states, the Qi's, go to states that are also indistinguishable from one another. For if not, then we could use a distinction between, say, the states delta Q1 of A and delta Q2 of A to distinguish between Q1 and Q2. But we already know that Q1 and Q2 are indistinguishable, so that can't happen. Thus, make the transition for state Q on input A be the representative for the indistinguishable states delta Q1A and so on. Let's work with the DFA that we constructed from the NFA that represented moves on a chessboard. We're going to make it easier to work with by renaming the states to be single letters. For example, A is the set containing only 1, and G is the set containing 1, 3, 5, 7, and 9. Here's a little trick for arranging pairs in a triangle so each pair appears exactly once. Notice that the rows are the states in order except for the last state, G, which doesn't appear there. Then the columns are labeled by the states in backwards order except for the first state, A. We begin the table of indistinguishabilities by marking each pair that consists of a final state and a non-final state. Here the final states are F and G, so pairs that have one of these and one of the other states, A through E, are marked. Let's look at the transitions on input R. Notice that the column for R has only states B and D. Since we have not yet distinguished B from D, there is no way input R can help distinguish other pairs of states at this point. However, we have more luck with input B. Some states go to final states on input B, namely C, D, E, and G, and the others, A, B, and F, go to non-final states. Thus, we can distinguish any of C, D, E, or G from any of A, B, or F. Some of these pairs are already distinguished, but we get 7 new pairs marked in red here. At the next step, we discovered 2 more distinguishable pairs, CD and CE. For example, C and D lead to F and G respectively on input B. So we know that whatever string W distinguishes F from G, B followed by W will distinguish C from D. Now we can mark the pair AB. These states transition on input R to B and D respectively, and we already know we can distinguish B from D. Unfortunately, D and E can never be marked because on both inputs they go to the same state. Okay. We are now done. We have distinguished every pair of states except for D and E. Moreover, we can never distinguish these states since they both go to D on input R and to G on input B. Thus, D and E form an indistinguishable group of states, and we can replace them by a representative. We choose the new state H as the representative, and all transitions from other states to D or E are replaced by transitions to H. The rows for D and E are replaced by a row for H. As D and E transition to D on input R, H transitions to itself on R. The transition on input B for H is to G, which is the same as it was for both D and E. As we mentioned, collapsing indistinguishable states to a single state goes a long way to finding the minimum state equivalent to a given DFA. But there is one other issue that indistinguishability doesn't address: the possible existence of unreachable states that are cluttering up the transition diagram or table. But it is easy to find such states, and we can either eliminate them from the original DFA, or we can eliminate them after merging indistinguishable states. It doesn't matter. Now we've done our best to combine states that we know how to combine, but it is in principle possible that there is some other smaller DFA that we can't get by combining states of our DFA, and fortunately, that can't happen, as we shall now see. Here's the proof that there is nothing smaller than the DFA we get by merging states and eliminating unreachable states. Suppose A is our DFA and B is a hypothetical equivalent with fewer states. Okay. Imagine we combine the states of A and B to form a larger DFA. It doesn't matter what the start state of the combined automaton is, but the final states are those of A and B. We need to use distinguishable in its contrapositive form. That is, if W distinguishes delta of QA from delta of PA, then surely AW distinguishes Q from P. So if Q and P are indistinguishable, then so are their successors on any input A. Here's an informal illustration of the proof technique. We start off with the fact that the start states of automata A and B are surely indistinguishable because the automata accept the same language. Now suppose the start states go to some states P and Q on input A. P and Q must be indistinguishable because if they were distinguishable, then we could distinguish the start states, and we know we cannot do that. Now, suppose Q and P go on input B to two other states, R and S. Then R and S must be indistinguishable for the same reason. Formally, we shall prove that every state Q of A is indistinguishable from some state of B. The proof is an induction on the length of the shortest string that gets you to Q from A's start state. Notice that because we eliminated unreachable states, we know there is such a shortest string. For the basis, the state of A that is reachable from the start state by a string of length 0, which is of course the start state itself. We know that this state of A is indistinguishable from the start state of B because the languages are the same. For the induction, assume the inductive hypothesis for strings shorter than W, and suppose W is a shorter string getting A to state Q. let W equal XA, that is, A is the last symbol of W and X is all the rest of W. We can apply the inductive hypothesis to X because it is shorter than W. We know X gets A to some state R that is indistinguishable from some state P of B. But then A takes state R on input A to state Q, and we know B takes state P on input A to some state, say, S. Then Q must be indistinguishable from S using the argument that we saw 2 slides ago. Okay. Now, we use the transitivity of indistinguishable to argue that no 2 states of A are indistinguishable from the same state of B. For if they were, they would be indistinguishable from each other. But A cannot have indistinguishable states because we merge them all constructing A. Thus, B has at least as many states of A, even though we started off assuming that there was no relationship between the automata A and B, except that they each accepted the same language. So that concludes the entire argument. It says that by throwing away unreachable states and then merging indistinguishable states, you get an automaton that is as small, that is, has as few states, as any other automaton for the same language.